Hey guys, a very good day to you all. In this video, we are going to understand what is hybridization and we will also see different types of hybridization. Now, before starting with this video, it is important that you all know what are orbitals and different shapes of orbital. Now, if you all do not know this guys, then don't worry, I've already uploaded a separate video on this. You can find the link of that video in the description box below, or you can simply click on the I button which is present on the right top corner of your screen. Okay. Now, many of you all know what are orbitals, but you all do not know the classification of orbitals. Okay. So, orbitals are basically classified into 4 different types. That is the S subshell, P subshell, D subshell and F subshell. This S subshell contains one orbital, that is S orbital. P subshell contains 3 orbitals, that is Px orbital, Py orbital and Pz orbital. D subshell contains 5 orbitals, Dxy orbital, Dyz orbital, Dzx orbital, dx square minus y square orbital and dz square orbital. And F subshell contains 7 different types of orbitals which you do not need to study as the shape is complicated and it is excluded in your portion as well. Okay, so basically throughout this video you need to keep in mind that inside S subshell there is only one type of orbital, inside P subshell there are 3 types of orbital and inside D subshell there are 5 types of orbital. Okay, now let me tell you all that any orbital can have maximum of 2 electrons in it. For example, S orbital can have 2 electrons maximum, Py orbital can have maximum of 2 electrons. Let's say dx square minus y square orbital will have maximum of 2 electrons. Okay, now coming back to our original topic, that is what is hybridization. In simple words, if I tell you all, hybridization is a process. For example, what happens during evaporation? During evaporation, as we all know that water changes from liquid form to gaseous form. Similarly, during hybridization, what happens is that atomic orbitals change from original form to their hybridized form. Now, how do they change from the original form to hybridized forms and what are different types of hybridized forms? This is what we are going to study in this video. Okay, now I am not directly going to tell you all the definition of hybridization, because if I directly tell you the definition of hybridization, you won't understand anything. Instead, what I am going to do is that I am going to help you all first understand the concept of hybridization, and then whenever I feel it is the appropriate time to define hybridization, at that time we will define hybridization. Okay, now obviously if hybridization is a process, every process has certain steps involved in it. Similarly, during hybridization also there are certain steps involved. Okay, and to understand the steps involved in hybridization, we are going to consider an example of beryllium fluoride molecule, BeF2. I repeat myself again. To understand the steps involved in hybridization, we are going to consider beryllium fluoride molecule as our example, BeF2. Okay, so let us consider the first step. The first step is the formation of an excited state. Okay, so as we all know that inside BeF2, beryllium is the central atom and the electronic configuration of Be is nothing but 1s2, 2s2. Now let us represent this according to the Hund's rule. Now as we all know that inside this S subshell there is only one orbital present. Therefore we draw one box. Okay, and inside this S subshell, as you can see, there are 2 electrons present. So to represent these 2 electrons, we draw 2 arrows, and these 2 arrows, as you can see, are in different direction, indicating that both of them are moving opposite to each other. One is moving anti-clockwise and another is moving clockwise. Okay, and inside this again, when you consider 2s2, inside this s subshell there is only one orbital present, if you remember, and therefore we draw one box. And inside this s subshell, as you can see over here, there are 2 electrons present. Okay, now what is the name of this orbital? We know that inside s subshell there are orbitals present, but since there are only one orbital present inside s subshell, therefore we give it the name as it is. We keep the name 1s and 2s respectively. We do not change the name because inside s subshell there is only one orbital present, and there is no need for you all to get confused and change the name. But when you consider p subshell, which we are going to consider very soon, and in that case we have to change the name of the orbital. Okay, so as can I say that inside this 1s orbital, there are 2 electrons present. Inside this 2s orbital there are 2 electrons present, and as mentioned earlier, in one orbital there can be maximum of 2 electrons. So as you can see over here, inside both the orbitals there are maximum of 2 electrons that are present. So guys, can I write the electronic configuration of beryllium as 1s2, 2s2, 2p0? Am I right? I'm obviously right, because in the second energy level there is s subshell present as well as there is p subshell present. But if you consider the first energy level, in the first energy level there is only s subshell present. Okay, now when you consider 1s2, we all know that in this s subshell there is only one orbital, therefore we give it the same name as 1s. And again, when you consider 2s2, we all know that inside s subshell there is only one orbital present, and we give it the same name, that is 2s. But if you consider the p subshell, if you consider this 2p0 and if you consider this p subshell, we all know that inside p subshell there are 3 orbitals present, and if you remember, their name is px, py and pz, and since they are present in the second energy level, therefore we write them as 2px, 2py and 2pz. Now since here we have only one orbital, therefore we draw one box, and inside this we can see there are 2 electrons present, so we draw 2 arrows. Again, here there is only one orbital and there are 2 electrons present, therefore we draw 2 arrows over here. Now here there are 3 orbitals, therefore you need to draw 3 squares. Clear? I hope you have understood up till here. Now what we observe is that the valency of Be, that is beryllium, is 2 in BeF2. So when you consider BeF2 molecule, the valency of Be is 2, and since its valency is 2, therefore there must be 2 unpaired electrons present. Now what is the meaning of this unpaired electrons? See, each orbital contains maximum of 2 electrons. So if in an orbital there is only one electron present, then we call that electron as unpaired electron. But here we are not having any unpaired electron present, as in both the orbitals we are having 2 electrons, and in both the orbitals we are having paired electrons. Can you see over here? In both the orbitals we are having paired electrons. We are not having unpaired electrons anywhere. But guys, we require 2 unpaired electrons. Now guys, can I say that if we require 2 unpaired electrons, which means that we require 2 orbitals in which there are only 1 electrons. Am I right? If you require 2 unpaired electrons, which means that we require 2 orbitals in which there are only 1 electrons each. Now, therefore, let me consider this on the next slide. Okay. Now, therefore, what happens is that one electron from 2s orbital one electron from 2s orbital is going to gain energy and it is going to get transferred to 2px. As you can see over here, one electron from 2s orbital has now gained energy and transferred to 2px. Why it has transferred to 2px? Because the valency of Be was 2, and since its valency is 2, therefore we require 2 unpaired electrons, and now here we have got 2 unpaired electrons. Now moving on, you can see over here that the electronic configuration of Be has also changed. It has changed from 1s2, 1s2 has remained as it is. It has changed from 2s2 to 2s1. Why it has changed to 2s1? Because 2s contains only one electron now, therefore we write it as 2s1. Whereas it has changed from 2p0 to 2p1. Why? Because now 2p1 contains one electron, and that one electron is present in 2px orbital. Okay, this p is a subshell, and in this 2px is a orbital, so that one electron is present in 2px orbital. And guys, this is called as the formation of an excited state. Why it is called as the formation of an excited state? Because as mentioned earlier, it has gained some energy and then transferred to the other orbital. It has gained energy and then transferred from 2s orbital to 2px orbital. Clear with this? Here we finish the first step of hybridization. Now let us move on to the second step of hybridization. The second step tells us mixing and recasting of atomic orbitals. Now what is the meaning of this? Let's understand. Okay, now guys, we have got 2 unpaired electrons. Now since we have got 2 unpaired electrons, which means that these 2 electrons are now eligible to form 2 bonds. Since we have 2 unpaired electrons, and we all know that unpaired electrons can form bonds and get paired up with some other atom. Clear? But guys, there is one problem over here. But the 2 bonds will not be equivalent. See, the bond formed by the electron which is present in the 2s orbital will not be equal to the bond formed by the electron which is present in the 2px orbital. Why it is not equal? Because obviously 2s orbital is not same as 2px orbital. Both the orbitals are same, there is an energy difference over there, and there are certain properties that are different. Okay, and we observe one thing, that in BeF2 both the bonds are equivalent. But guys, in BeF2 we observe that both the bonds are equivalent. But here we are getting a situation where both the bonds cannot be equivalent. So in this scenario, what happens is that this 2s orbital, see this 2s orbital is going to get combined with 2px orbital. It is going to get merged, somewhat like merged, or get combined with the 2px orbital. As you can see over here, this 1s2 as it is, then this 2s has now got combined with 2px. Can you see over here? Both these orbital, this orbital has got combined with this orbital. See, they have got combined with each other, and the new name of the orbital is given as 2sp. Why it is given as the 2sp? Because as you can see over here, single s orbital is combining with the p orbital. See, p subshell orbital. Therefore, see, s subshell orbital is combining with the p subshell orbital. Therefore, the name is given as 2sp. And guys, as you can see over here, now the orbitals have become equivalent and the bonds formed by them will also be equal. So this is called as mixing and recasting of atomic orbitals. And guys, this 2sp, we get 2 we get 2 2sp orbitals. हम लोग को दो 2sp ऑर्बिटल्स मिलते हैं एंड वी गेट दिस 2 ऑर्बिटल्स, दिस हम लोग को जो दो 2sp ऑर्बिटल्स मिले हैं उन लोग को बोलते हैं hybridized orbitals. These both orbitals that we have got are called as hybridized orbitals. Clear? Now, if you observe one thing over here, one pure orbital, this 2s is a pure orbital, has got mixed with another pure orbital. This 2px is also pure orbital. So guys, can I say that when there is a mixing and recasting of two pure orbitals, so when two pure orbitals mix with each other, we get two hybridized orbitals. Now if I ask you one question, if 4 pure orbitals combine with each other, then how many hybridized orbitals we will get? We will get obviously 4 hybridized orbitals, as you can see over here. Clear with this, guys? And guys, you can see over here that when s orbital combines with the p orbital, this is the hybrid orbital that we get. See this sp orbital that we get. This is one sp and this is second sp orbital. And they both are inclined at 180 degree to each other. Now why they are inclined at 180 degree to each other and why is their shape like this? This we are going to understand in the next video, where we will see VSEPR, valence shell electron pair repulsion. When we understand that, at that time you will get to know why their structure is like this. In this video we are not concerned with the molecular structure. Our main aim is to understand what is hybridization, and I hope that you have got what is hybridization. And what is their shape, that we will see in the next video. So don't worry about that. Now guys, let us understand the salient features of hybridization. So the first point, atomic orbitals of same atom can take part in hybridization. As you can see, as you have seen over here, the orbitals of same atom, that is Be, were taking part in hybridization. Okay. So there is no much difficult point in this. The second point tells us that atomic orbitals having comparable energies can only undergo hybridization. This is an important point, as in our example 2s was getting combined with 2px. They both were undergoing hybridization, but 2s and 2px have comparable energies, which means that the energy difference between them is less. Therefore, hybridization was possible between those two orbitals. If hybridization is, if the energy difference is more, then hybridization is not possible. Clear? The third point, this we have discussed just now, that number of hybrid orbitals formed is equal to the number of orbitals taking part in hybridization. That we have discussed, and I hope that you all have understood this point. It's an important point, in fact. The fourth point tells us that the shape of hybrid orbitals is different from pure orbitals. As you can see over here, that the shape of the pure orbital, that is s orbital, is spherical in shape, this p orbital has a dumbbell shape, and this sp orbital has some other shape. Don't forget to consider this inside part also. Okay, so this is not as same as p orbital, but there is some difference over here as well. The fifth feature tells us that the covalent bonds formed by hybrid orbitals are stronger than those by pure orbitals. Now what is the meaning of this? See, as mentioned earlier, that even 2s can form a covalent bond, even 2px can form a covalent bond, but the bonds formed by 2sp and 2sp will obviously be stronger than the bonds formed by 2s and 2px respectively. So hybrid orbitals are going to form a stronger covalent bond as compared to the pure orbitals. So here I have not discussed the points, salient features regarding to the structure, because this we are going to understand in the next video. Here again, repeat myself again, here our main motive is to understand what is hybridization. Now moving on, I think that's now it's time for us to understand the types of hybridization. And as we understand each type of hybridization, we are going to consider an example of some molecules so that we understand that hybridization in a much better way. Okay, so let's start with the first type of hybridization, that is sp hybridization. And in order to understand this hybridization, we are going to consider an example of ethene C2H2. Okay, now let us consider the carbon atom, and the electronic configuration of carbon atom is 1s2, 2s2, 2p2. Now as we all know that inside this s subshell there is only one orbital present. Therefore we draw a one box, and there are two electrons present, and we all know that in one orbital there can be two electrons. So we draw two arrows. Now inside this s subshell there are again two electrons present. So inside s subshell there is one orbital, and inside that one orbital there are two electrons present, and we all know that inside one orbital there can be maximum of two electrons. So we draw two electrons. Now we all know that inside this p subshell there are three orbitals, px, py, pz. So we draw three boxes, and we all know that since there are two electrons present in p subshell, therefore first it will singly fill the orbitals. First one electron will fill the 2px orbital, and the second electron will fill the 2py orbital. This is the Hund's rule. Do not make a mistake over here by writing this second electron in 2px only. No, first each orbital will get one electron each, and then they will get double electrons. Hund's rule, if you all remember. Then moving on, the valency of carbon is 4 in ethene, whatever you pronounce. But here if you will observe that since the valency of carbon is 4, which means that we require 4 unpaired electrons, but here we are having only 2 unpaired electrons. So guys, can I say if you require 4 unpaired electrons, in other words, can I say that we require 4 half-filled orbitals, which means that we require 4 orbitals in which there must be 1 electron each. So what happens is that again, one electron from this 2s orbital is going to get shifted by gaining energy. It is going to get shifted into 2pz, as you can see over here. See, this 1s2 as it is, 2s2 has now changed from 2s2 to 2s1 because it has now only one electron left, and that one second electron has now jumped to 2p z orbital. It will not jump to 2px or 2py because according to the Hund's rule each orbital will get one electron first. Therefore it will jump to 2pz. I've considered this on a new slide now. Now guys, what happens in ethene is that one 2s orbital gets combined with 2pz orbital. If you remember that electron has gone to the 2pz orbital. So this 2s orbital and this 2pz orbital get combined, and the new electronic configuration becomes something like this. See, as you can see over here, this 2s has combined with 2pz, and the new name of the orbital is 2sp, and this 2px and 2py are going to remain as it is. Nothing is going to happen to them. See over here, this 1s orbital has also remained as it is. Now this 2sp and 2sp are called as the hybridized orbital, and this 2px and 2py are called as the unhybridized orbital because they have not gone on any change and they are still in their pure form. Clear with this? And guys, this is called as sp hybridization of carbon atom in ethene. And guys, well, remember we have already done this sp hybridization in the molecule of BeF2. If you have watched the video carefully, you will have noticed that we have already done the sp hybridization in the molecule of BeF2. Now moving on to the second type, sp2 hybridization. Wait, let me tell you all. I hope you have understood why the name is given as sp hybridization, because one s subshell orbital, this 2s, is combining with one p subshell orbital, 2pz. Therefore, the name is given as hybridization. Second type is sp2 hybridization, and here we are going to consider an example of BF3. Okay, BF3, boron fluoride. Now moving on, guys, the electronic configuration of center atom, that is boron, is nothing but 1s2, 2s2, 2p1. We all know that inside this S subshell there is only one orbital present, that is 1s. Therefore, we write 1s over here. Inside this S subshell, 2s subshell, if you consider 2s2, inside this S subshell there is only one orbital present, and we give it the same name, that is 2s. Inside this P subshell there are three orbitals present, px, py, pz. Therefore, we name them as 2px, 2py and 2pz. This 2 just indicates the energy level, okay, in which energy level they are present. Now, since here there is only one orbital, therefore we draw one box, and inside this S subshell there are two electrons present. Therefore, we all know that inside one orbital there can be maximum of 2 electrons. We draw those 2 electrons. Inside this S subshell also there are 2 electrons present, and in one orbital there can be 2 electrons. Therefore, we draw them. Next, inside P subshell there are 3 orbitals. Therefore, we draw 3 boxes first. Then inside P subshell there is only one electron present, and that one electron will go to 2px orbital. Okay. Now 2py and 2pz do not have any orbital because there are no electrons present. Clear? Moving on, we observe that the valency of boron is 3 in BF3, and if the valency is 3, which means that we require 3 unpaired electrons. We require 3 unpaired electrons, and if you require 3 unpaired electrons, guys, can I say we require 3 orbitals with 1 electron each? Am I right? We require 3 orbitals with 1 electron each. Now if you want this, so what is going to happen is that 1 electron from 2s orbital is going to gain energy, and it will get transferred to 2py. Okay, so the new electronic configuration becomes 1s2 as it is. 2s2 will now change to 2s1 because, as you can see, there is now only one electron present, and the second electron will go to 2py, and 2p1 now changes to p2 because it has now gained one extra electron. I hope this was easy. Now, what happens is that, let me consider this on another slide. Now what is going to happen is that this 2s orbital is going to get combined with 2px and 2py orbital. Okay. Now since it gets combined with 2px and 2py orbital, it is going to now form an hybridized orbital, and the name of that hybridized orbital, as you can see over here, 3 pure orbitals are combining. Therefore, we are getting 3 hybridized orbitals, and this 1s2 as it is, and the name of the hybridized orbitals will be sp2, sp2, sp2. Why the name is sp2? Because one orbital from S subshell is combining with 2 orbitals, 2px and 2py, which are present in the P subshell. Therefore, the name is sp2. 2 indicates 2 orbitals from P subshell. Clear? And guys, this is called as sp2 hybridization of, here there is a mistake, it is B, boron, not Be, atom in BF3. Clear with this? I hope this was also easy. Now I think the process has become easier for you all, and you will understand it ahead very easily. The third type is the sp3 hybridization, and here we are going to consider the example of methane CH4. Let us consider the center atom, carbon. The electronic configuration of carbon is nothing but 1s2, 2s2, 2p2. Now inside this S subshell there is one orbital present, and we name that orbital as 1s. Inside this S orbital there is again one orbital present. We name that orbital as 2s. Inside this P subshell there are 3 orbitals present. We name them as 2px, 2py, 2pz. And guys, since here there is only one orbital, therefore we draw one box, and inside this one orbital there are 2 electrons, as you can see over here. Again, similar thing happens over here. We draw one box and there are 2 electrons present. but here there are 3 orbitals, therefore we need to draw 3 boxes, and in 2p2 there are 2 electrons and 2 orbitals will get 1 electrons each. Clear? According to Hund's rule. Now moving on, what we observe is that in methane the valency of carbon is 4. Okay, so in methane the valency of carbon is 4, which means that we require 4 unpaired electrons. Now since we require 4 unpaired electrons, which means that we require 4 orbitals with 1 unpaired with 1 electron each. So in this scenario, what is going to happen is that 1 electron from 2s is going to get jumped to 2pz. As you can see over here, 1 electron has jumped to 2pz, and now this 2s2 becomes 2s1 because it has now only 1 electron, and this 2p2 becomes 2p3 because it has gained 1 electron. And this is the excited state, if you remember. Why it is called as excited state? Because it has gained energy. Now let me consider this on another slide. Now here, what happens is that this 2s gets hybridized with 2px, 2py, 2pz. In methane, 4 pure orbitals are going to get hybridized, and after they get hybridized, they are going to form a hybridized orbital named as sp3. Now why it is given the name as sp3? Because 1 orbital from s subshell is combining with 3 orbitals from p subshell. Therefore sp3, 3 indicates 3 orbitals from p subshell, and this is how they are going to look like. They are 4 electrons as it is. Clear? And this type is called as the sp3 hybridization. Now I think the process has become easier for you all. Now moving on to the next one, sp3d hybridization in PCl5. So here guys, in PCl5 we are going to consider the center atom, that is phosphorus, and the electronic configuration of phosphorus is nothing but 1s2, 2s2, 2p6, 3s2, 3p3 and 3d0. I can write 3d0, am I right? I am not doing anything wrong over here. Now neglect this inner energy level. We are going to consider only the outer energy level, that is 3, because if you observe up till now, there was no changes observed in the inner energy level. So the only changes observed was in the outer energy level, because the outer energy level electrons are responsible for forming covalent bonds. Okay, so let's consider only third energy level. Just neglect them for a while because we are having a space constraint over here. Okay, so this s subshell is divided into 1 orbital and we name it as 3s. This p subshell is divided into 3 orbital. There are px, py, pz, and these 3 indicates the energy level, and this d is divided into 5 orbitals that I have not written over here. I will write it after words ahead as we move in the video, because here I am having less space and they cannot be fitted. Now since there is only 1 orbital, therefore I draw 1 square, and inside this 1 square there are 2 electrons, as you can see over here. Now if you consider over here, there are 3 orbitals present and there are 3 electrons, which means that each orbital will get 1 electron respectively. Okay, clear with this? And here this d although contains 5 orbitals, but they are not having any electrons because there are no electrons left. Now moving on, what we observe is that the valency of phosphorus is 5 in PCl5, which means that guys, can I say we require 5 unpaired electrons, and to have 5 unpaired electrons we require 5 orbitals with 1 electron each. Am I right? We require 5 orbitals with 1 electron each. So in order to have that 1 electron, this 1 electron from 3s is going to get jumped to 3p6x. Let me show you all over here only. 1 electron from 3s is going to get jumped to 1 orbital of 3dxy. Okay, so as you can see over here, the electron has jumped to 3dxy. Now guys, can I say that we have got 5 unpaired electrons? Now some people might get a doubt that the electron from 3s should have jumped to 3px. No, if it jumps to 3px, then we won't be having unpaired electron. We want unpaired electrons. We require 5 unpaired electrons. So this is possible only when this electron jumps to 3D xy. Clear with this? Now let me consider this over here. Now, as we all know that this 3s orbital, this 3px, 3py, 3pz and this 3dxy, they are obviously not having similar energies, and phosphorus cannot have different types of bond with five chlorine atoms. Okay, it must be equal to each and every chlorine atom. It cannot be biased. Okay, so what is going to happen is that this 3s, 3px, 3py, 3pz and 3dxy, they are going to they will undergo hybridization. Okay, so they will undergo hybridization, and this is what you get. And the name of the hybridized orbitals will be sp3d. Why? Because if you observe over here, one s orbital, only one orbital from s subshell is taking part in hybridization, whereas there are three orbitals from p subshell that are taking part in hybridization, and only one orbital from d subshell is taking part in hybridization. Therefore, s, p3 and d, as you can see over here. Now guys, don't get confused that here this 1s2, 2s2, 2p6 are present. They are there, but I have not written because of the space constraint. Otherwise you all will think that they are gone. Now this is called as the sp3d hybridization of phosphorus in PCl5. So guys, I hope that this fourth type is also clear for you all. Moving on to the fifth type, the last type, that is the sp3d2 hybridization. And to understand this, we are going to consider an example of SF6. Now guys, let us consider the center atom, that is sulfur. The electronic configuration of sulfur is nothing but 1s2, 2s2, 2p6, 3s2, 3p4 and 3d0. Because in third energy level there is d subshell present. Okay. Now, as you can see over here, inside this 3s subshell there is only one orbital present. Therefore, we draw one square, and inside this one square there are two electrons present. And as you can see over here, inside this 3p there are four electrons that are present. And since there are four electrons present, therefore one electron will fill each orbital, and the fourth electron will go in 3px. Now guys, what happens over here is that the valency of sulfur is 6 in SF6. Now since the valency is 6, which means that we require 6 unpaired electrons. And to have 6 unpaired electrons, what is going to happen is that one electron from 3s orbital is going to get jumped to 1d orbital, and one electron from here, this 3px, is going to get jumped to another d orbital. As you can see over here, see, they have jumped, and now we are having 6 unpaired electrons, which means that we are having 6 half-filled orbitals. Clear with this? Now what happens over here is that obviously sulfur cannot be biased to any fluorine atom. It must be equivalent to all the 6 fluorine atoms. Therefore, they are going to undergo hybridization. This 3s orbital will undergo hybridization with this 3px, 3py, 3pz, plus there will be 3dxy, 3dyz. Clear? Now, after they undergo hybridization, the new orbitals that will be formed, the name of those orbitals will be 3sp3d2. Now why s? Because only one orbital from s subshell is taking part, 3 orbitals from p subshell are taking part, as you can see over here, and 2 orbitals from d subshell are taking part, therefore d2. And as you can see over here, there are 6 hybridized orbitals that are being formed, and each contain one unpaired electron. Clear with this? And here we finish the types of hybridization as well. And guys, now at the end of the video, I feel it is now the right time to define what is hybridization. Okay, so here comes the definition of hybridization. let us understand this definition. Okay, so basically hybridization is the process which I have already told you all of what? It is a process of mixing and recasting of whom? It is a process of mixing and recasting of atomic orbitals of the same atom. As you have seen, it is the mixing and recasting of atomic orbitals of the same atom which have slightly different energies. So guys, I hope you have understood up till here. It is a process, and it is a process of what? Mixing and recasting of whom? Of atomic orbitals of the same atom with slightly different energies to form equal number of new orbitals. That is nothing but the hybridized orbitals that I was speaking throughout the videos. And these hybridized orbitals have equivalent energy, maximum symmetry, and definite orientation in space. So guys, I hope that you have understood what is hybridization and the different types of hybridization. If you have liked this video, then go check out my channel where I have uploaded physics and chemistry videos. They might be helpful for you all. And guys, thank you for watching this video.